Hey there, fellow adventurers. Today we're heading somewhere most maps forgot existed. A place where swamps swallow entire savannas, rivers carve through endless jungle, and one creature has haunted human nightmares for centuries. We're talking about Guyana, South America's best-kept secret, and its most infamous resident, the giant anaconda. You know, that snake your uncle swears he saw in a totally real documentary that was definitely just a horror movie from 1997. Here's the thing. Somewhere in those flooded forests, there's a serpent so massive that local tribes described walking for 2 days along what they thought was a wall, only to realize it was a single snake's body. Sounds like absolute nonsense, right? Well, that's exactly what a team of researchers set out to prove, or disprove, armed with drones, underwater robots, and probably way too much confidence. Their mission? Hunt down the truth behind the legend. So buckle up, because we're about to wade through some of the most remote wilderness on Earth, meet creatures that make your local zoo look like a petting farm, and find out if those impossible stories hold any weight. Before we dive in, smash that like button if you're ready for this jungle madness, and drop a comment telling me where you're watching from. I genuinely want to know who's crazy enough to join me on this expedition. Let's go. Now, before we go chasing after giant snakes like a bunch of adrenaline junkies with questionable life choices, we need to understand exactly where we're heading. Because Guyana isn't just some random patch of jungle you can stroll through with a machete and a dream. This place is basically nature's version of a labyrinth designed by someone who really didn't want visitors. Picture this. A landmass roughly the size of Britain, tucked into the northeastern shoulder of South America, sandwiched between Venezuela, Brazil, and Suriname. Sounds manageable, right? Wrong. About 80% of this country is covered in dense primeval rainforest that has been doing its thing since long before humans decided walking upright was a good idea. The remaining 20% consists of coastal plains, savannas, and a bewildering network of rivers, creeks, swamps, and flooded grasslands that seem to have been designed specifically to confuse anyone trying to navigate them. Good luck finding a road sign out here. Nature doesn't believe in GPS. The thing that makes Guyana truly special, and by special I mean simultaneously breathtaking and terrifying, is its water system. We're not talking about a few rivers here and there. We're talking about thousands upon thousands of waterways that crisscross the landscape like veins running through a living organism. The Essequibo River alone stretches over 1,000 kilometers, making it one of the longest rivers in South America that most people have never heard of. It's basically the Amazon's shy cousin who doesn't post on social media. Branching off from this main artery are countless tributaries, each one feeding into marshes, oxbow lakes, and seasonal floodplains that create one of the most complex aquatic ecosystems on the planet. Now here's where things get interesting, and by interesting I mean absolutely chaotic. Guyana operates on 2 distinct seasons that transform the entire landscape in ways that would make any Hollywood special effects team jealous. The dry season, which typically runs from September through April, is when the country reveals its secrets. Rivers shrink back to their core channels, exposing muddy banks, sandbars, and shallow pools that become natural gathering spots for wildlife. Imagine draining a bathtub and watching everything that was hidden underneath suddenly come into view, except instead of lost toys and hair clumps, you're looking at caimans, capybaras, and yes, our scaly friends the anacondas. During these dry months, the savannas of the Rupununi region transform into something resembling an African wildlife documentary. Vast grasslands stretch toward the horizon, punctuated by scattered termite mounds that rise like miniature skyscrapers built by the world's most industrious insects. Cattle ranches dot the landscape, their herds grazing peacefully alongside wild deer, giant anteaters, and the occasional jaguar who hasn't yet received the memo about property boundaries. The water that remains becomes concentrated into specific ponds, lagoons, and river stretches, creating natural hotspots where animals have no choice but to gather. It's like nature's version of a singles bar, except everyone's there because they're thirsty, and some of the patrons happen to be apex predators. This concentration effect is precisely what makes the dry season prime time for wildlife observation. When you've got dozens of caimans basking on a single stretch of riverbank, or a congregation of Jabira storks stalking fish in a shrinking pond, you don't need to go searching for action. The action comes to you. Researchers studying large predators absolutely love this time of year because it eliminates the needle in a haystack problem. Your subjects aren't scattered across a million acres of flooded forest. They're right there, predictably hanging out at the local watering hole like regulars at a neighbourhood pub. But here's the catch, and there's always a catch when you're dealing with tropical wilderness. The dry season doesn't last forever, and when it ends with all the subtlety of a fire alarm at 3 in the morning. The wet season arrives somewhere between May and August, though Mother Nature apparently didn't get the memo about sticking to a schedule. Some years the rains show up fashionably late. Other years they crash the party 4 weeks early, catching everyone off guard. Weather forecasting in Guyana is less of a science and more of a polite suggestion that the sky might do something eventually. When the rains do come, they come hard. We're talking about deluges that would make Noah consider building a bigger boat. The sky opens up and dumps water with an intensity that seems almost personal, as if the clouds have been saving up all year just to make this moment count. Within weeks, those peaceful rivers that had shrunk to manageable streams suddenly remember their true purpose. They swell, overflow their banks, and spill across the landscape with complete disregard for human concepts like roads, buildings, or carefully planned research expeditions. The transformation is nothing short of spectacular. Those savannas that looked like African plains just a few months ago, now they're inland seas stretching as far as the eye can see. The Rupununi floods so extensively that you can travel by boat through areas that were recently cattle pastures. Trees that stood on dry ground now have their trunks submerged up to the waterline, creating a flooded forest that looks like something from a fever dream. The entire ecosystem essentially hits the reset button, redistributing nutrients, reconnecting isolated populations, and giving aquatic species free rein to expand their territory into places that were previously off limits. For the animals that call Guyana home, this seasonal rhythm isn't some inconvenience to be endured. It's the fundamental beat that dictates their entire existence. Fish spawn when the floods come, using the newly inundated grasslands as nurseries where their young can grow with reduced predation pressure. Wading birds time their breeding cycles to coincide with falling water levels, when concentrated fish populations make feeding their chicks a relatively easy task. Even the insects get in on the action, with mosquito populations exploding after the rains in numbers that would make any tropical disease researcher simultaneously excited and deeply concerned. And then there are the anacondas. These massive constrictors have evolved to exploit both seasons with remarkable efficiency. During the dry months, they congregate around permanent water sources, waiting patiently for prey to come to them. A 7-meter snake doesn't need to be particularly active when lunch basically delivers itself to your doorstep. But when the floods arrive, the rules change entirely. Suddenly, the anaconda's domain expands exponentially. They can travel through flooded forests and submerged grasslands, accessing areas that were previously unreachable, hunting in conditions where their aquatic prowess gives them a massive advantage over terrestrial prey. Understanding this seasonal dynamic is absolutely crucial for anyone hoping to study, film, or simply survive an encounter with Guyana's wildlife. Show up at the wrong time of year and you might find yourself wading through chest-deep water where a road used to be, or alternatively staring at a cracked mudflat where you were promised a wildlife-rich lagoon. The local guides, many of whom come from indigenous communities that have lived here for thousands of years, read these seasonal signs the way most of us read weather apps, except their predictions actually work. The indigenous peoples of Guyana, including the Makushi and Wapishana communities of the Rupununi, have developed an intimate knowledge of how these water systems function. They know which ponds retain water year-round and which ones dry up completely. They understand when certain fish species will be running, when the fruits that attract wildlife will be ripe, and perhaps most importantly for our purposes, where the big anacondas like to hang out during different seasons. This isn't mystical ancient wisdom, though it might as well be given how accurate it tends to be. It's simply what happens when a community spends generations paying very close attention to the world around them, because their survival literally depends on it. For modern researchers arriving with their drones, GPS trackers, and waterproof laptops, this traditional knowledge represents an invaluable shortcut. You could spend years cataloguing every pond and creek in the Rupununi, mapping seasonal flood patterns, and figuring out wildlife movement through sheer trial and error. Or you could sit down with an elder who grew up fishing these waters and learn more in an afternoon than 6 months of satellite imagery analysis would reveal. Smart expeditions do both, combining cutting-edge technology with time-tested local expertise in a partnership that acknowledges each approach has something the other lacks. The water system also creates natural barriers and corridors that shape how species move across the landscape. During the dry season, certain areas become isolated, surrounded by dry land that aquatic animals cannot cross. These isolated pools turn into temporary refuges where you might find unusual concentrations of fish, caimans, turtles, and yes, snakes. Scientists call these drought refugia, which is just a fancy way of saying everybody who needs water ends up in the same place when the water gets scarce. It's like musical chairs, except the music is monsoon rain, and losing means dehydration. Conversely, during the wet season, the floods create connectivity between waterways that were previously separate. Fish can move from one river system to another. Predators can access hunting grounds that were off-limits for months. This seasonal connectivity is essential for maintaining genetic diversity in populations and allowing species to recolonize areas where local populations might have died out. It's essentially nature's way of shuffling the deck every year, making sure the game stays interesting and no single group gets too comfortable. For anyone planning an expedition into this territory, timing becomes everything. The sweet spot for most wildlife observation is the transition period between wet and dry seasons, when water levels are dropping but haven't yet reached their lowest point. You've still got enough water to navigate by boat, but the wildlife is starting to concentrate around the remaining pools. The vegetation isn't completely dried out and brown, so things actually look good on camera. And perhaps most importantly, you're not dealing with either the brutal heat of peak dry season or the constant deluge of the heavy rains. Getting the timing wrong can turn a promising expedition into a logistical nightmare. Show up too early in the wet season, and you'll spend most of your time bailing water out of boats, cursing at mosquitoes, and watching your equipment develop mysterious tropical fungi. Arrive too late in the dry season, and you might find that the water body you came to study has turned into a cracked mudflat, with a few desperate fish flopping in what remains. The window of optimal conditions is surprisingly narrow, and it shifts from year to year depending on factors that even the most sophisticated climate models struggle to predict. This is why serious research expeditions typically involve multiple visits spread across different seasons and years. One trip can give you a snapshot, but understanding the full picture requires seeing how the system behaves under different conditions. The anaconda you spotted lounging in a pond during November might have moved 20 kilometers away by February. The caiman population that seemed enormous during the dry season might disperse so thoroughly during the floods that you'd swear they'd all vanished. Building a complete understanding of how species use this dynamic landscape requires patience, persistence, and a willingness to get very, very wet. The hydrological complexity also creates habitats that exist nowhere else on Earth. The seasonally flooded savannas of the Rupununi, for instance, support a community of plants and animals specifically adapted to this boom and bust water cycle. Some fish have evolved the ability to survive in damp burrows during the dry months, emerging only when the floods return. Certain trees have developed root systems that can tolerate both complete submersion and extended drought. Even the soil has been shaped by this cycle, with nutrient patterns reflecting thousands of years of annual flooding and recession. All of this might seem like a lot of geographical detail for a story about hunting giant snakes, but here's the thing. You cannot understand the anaconda without understanding its world. These animals are not separate from their environment. They are shaped by it, dependent on it, and perfectly adapted to exploit its peculiarities. The seasonal floods that create such challenges for human visitors are precisely the conditions that allowed anacondas to evolve into the giants they are today. The complex waterway network that confuses our GPS devices is the same network that provides anacondas with endless hunting opportunities and virtually unlimited places to hide. So before we start deploying our high-tech gadgets and stomping through the jungle looking for oversized reptiles, we need to acknowledge that we're entering a world that operates on completely different rules than what most of us are used to. This isn't a zoo where the animals stay conveniently in their enclosures. This isn't a nature documentary where everything happens within a 2-hour runtime. This is millions of acres of wild, wet, constantly changing terrain that has been producing giant snakes for millions of years before we showed up with our cameras and our questions. The water dictates everything out here. It determines where animals can live, how they can move, what they can eat, and ultimately whether researchers can even reach them. Respect the water, understand the seasons, and work with the local knowledge rather than against it. That's the formula for actually accomplishing something in this environment. Ignore any of those elements and you'll find yourself stuck, lost, or quite possibly face to face with something large and hungry, while being extremely unprepared for the encounter. With our geographical orientation complete, we can finally start talking about how modern technology is being deployed to solve a mystery that has puzzled explorers for centuries. Because as it turns out, finding a giant snake in a landscape this complex requires some seriously creative problem solving. So we've established that Guyana is essentially nature's obstacle course, designed to humble anyone who thinks finding a giant snake should be straightforward. The obvious question becomes, how do you actually locate a creature that can grow longer than a school bus in a landscape that seems specifically engineered to hide things? The answer, as it turns out, involves enough gadgets to make James Bond feel underprepared. Modern anaconda research has evolved far beyond the traditional approach of wade into swamp, hope for the best, try not to die. Today's expeditions look more like NASA mission control crossed with a high-end electronics store. We're talking drones, underwater robots, thermal imaging cameras, satellite tracking systems, and enough battery packs to power a small village. The jungle might not have changed much in the last million years, but our ability to explore it certainly has. Let's start with the eyes in the sky. Drones. These aren't your neighbour's annoying Christmas present that crashed into a tree after 15 minutes. We're talking about specialised unmanned aerial vehicles equipped with high-definition cameras, GPS transmitters, and flight systems capable of navigating through jungle canopy gaps that would make a helicopter pilot nervous. These machines can survey areas in hours that would take ground teams weeks to cover on foot, assuming the ground teams didn't get lost, stuck in mud, or distracted by something trying to eat them. The real magic happens in how these drones are controlled. Forget those clunky joysticks that make you feel like you're playing a video game from 1995. Modern expeditions use what can only be described as cyber gloves, specialized controllers that translate hand movements into precise drone maneuvers with almost surgical accuracy. Wave your finger to the left, the drone banks left. Tilt your palm down, it descends. It's like having telekinetic powers, except the powers cost several $1,000s and require regular charging. The precision matters because when you're trying to photograph a specific pond through a gap in the forest canopy, while avoiding branches, power lines that somehow exist out here, and the occasional confused bird, you need control that goes beyond. Up, down, left, right. But here's the thing about searching for anacondas from the air. These snakes spend most of their time in or underwater. A drone flying overhead might catch a glimpse of a basking snake on a riverbank during the right conditions, but it's essentially useless for finding animals submerged in murky tropical water. This is where the underwater robots enter the picture, and honestly, this is where things get genuinely cool. ROVs, or remotely operated vehicles, are essentially miniature submarines equipped with cameras and lights that can be piloted into aquatic environments too dangerous, too murky, or simply too snake-infested for human divers. Picture a waterproof drone the size of a football, trailing a cable that transmits live video back to a laptop sitting safely in a boat above. These little machines can descend into the depths of jungle lagoons, navigate through submerged vegetation, and capture footage of whatever's lurking down there, all while the researchers stay comfortably above water, presumably not being constricted by anything. The video feeds from these ROVs get transmitted directly to researchers' equipment in real time, which sounds straightforward until you remember that we're operating in a jungle where the sun can turn your laptop screen into a useless mirror of glare. The solution? Specialized video goggles that block out ambient light while displaying the camera feed directly in front of your eyes. It looks absolutely ridiculous. Imagine a scientist sitting in a dugout canoe wearing what appears to be a virtual reality headset, while everyone else sweats in the tropical heat. But it works remarkably well. You can see exactly what the underwater robot sees, even at high noon when the equatorial sun is doing its absolute best to blind everyone. Thermal imaging adds another layer to this technological sandwich. Anacondas, like all reptiles, are cold-blooded, which means their body temperature roughly matches their environment. This should theoretically make them invisible to thermal cameras, right? Wrong, and here's why. While a snake that's been sitting in cool water for hours might indeed blend into the thermal background, one that's been basking in the sun will retain that heat for quite a while. More importantly, the areas where anacondas like to rest often have slightly different thermal signatures than the surrounding environment. A warm mud bank, a sun-heated rock, a decomposing log generating bacterial heat. Researchers have learned to read these thermal landscapes like a map, identifying the spots most likely to harbour their quarry. The thermal cameras also prove invaluable during night operations. Anacondas are primarily nocturnal hunters, which means the best time to observe their natural behaviour is precisely when human vision becomes essentially worthless. Infrared cameras transform this darkness into a heat map where warm-blooded prey animals glow like beacons, and the cooler reptilian predators appear as distinct thermal signatures against their environment. Watching a monitor as a warm yellow blob representing a capybara wanders near a cooler blue-green shape that turns out to be a massive snake. That's the kind of footage that makes all the technological investment worthwhile. Then there are the miniature remote-controlled vehicles that operate on land. Think of them as toy cars that went to engineering school and got very, very serious about their purpose in life. These wheeled robots, often no bigger than a shoebox, can be equipped with thermal sensors and cameras and sent into areas too dense, too dangerous, or too likely to contain large predators for human researchers to casually stroll through. The beauty of these machines is that they're essentially invisible to heat-sensing animals. Unlike a warm human body radiating infrared light like a walking advertisement, these cold metal scouts register as just another piece of environmental background noise. This invisibility factor cannot be overstated. Anacondas hunt using specialized pit organs that detect infrared radiation. Essentially, they can sense the body heat of nearby animals. A researcher creeping through the undergrowth at night is basically a glowing target from the snake's perspective. A small robot made of aluminum and plastic? That's just another rock as far as the snake's heat sensors are concerned. This allows for observations and approaches that would be impossible for human researchers, letting scientists document behaviors that would normally be interrupted by the animals detecting their warm-blooded presence. GPS tracking represents perhaps the most significant technological advancement for long-term anaconda research. Getting a tracking device onto an anaconda is exactly as challenging as it sounds. You need to catch the snake first, which is a process we'll discuss later, and which involves far more wrestling than most scientific fieldwork. But once a transmitter is attached, it sends regular location updates via satellite, allowing researchers to build a picture of how these animals move across the landscape over weeks, months, and even years. The data from GPS tracking has revolutionized our understanding of anaconda behavior. We now know that these snakes can travel surprisingly long distances during certain seasons, moving between dry season refuges and wet season hunting grounds in patterns that follow the changing water levels. We've learned that individuals often return to the same specific locations year after year, showing a degree of site fidelity that suggests these animals have much better mental maps of their territory than anyone previously assumed. We've discovered that males will travel remarkable distances during breeding season, apparently able to detect female pheromones from kilometers away. All of this technology creates what researchers call a multi-layered surveillance approach. Drones provide the wide-angle view, identifying promising areas and tracking water level changes. Ground robots offer close-up reconnaissance without disturbing the targets. Underwater ROVs explore the aquatic realm that these semi-aquatic snakes call home. Thermal cameras extend observations into the nighttime hours when anacondas are most active. GPS trackers provide longitudinal data about movement patterns over extended periods. And the specialized viewing equipment, the video goggles, the enhanced displays, the satellite uplinks, tie all of this information together into something approaching a complete picture. But here's the humbling reality that every technologically equipped expedition eventually confronts. All of this expensive, sophisticated equipment is ultimately limited by the environment it operates in. Drones get tangled in branches. ROVs get stuck in submerged vegetation. GPS signals struggle to penetrate dense jungle canopy. Batteries die at the worst possible moments, usually when you're about to record something amazing. Humidity fogs camera lenses. Insects crawl into equipment in ways that seem to defy the laws of physics. The jungle doesn't care how much money you spent on your gadgets, it will find a way to humble your technology. This is precisely why the most successful modern expeditions combine cutting-edge technology with something far older and arguably more reliable. Local knowledge passed down through generations of people who have lived in this landscape since long, before electricity existed. Which brings us to perhaps the most valuable resource any anaconda researcher can access: the wisdom of the indigenous communities who call Guyana home. The indigenous peoples of Guyana have been living alongside giant anacondas for thousands of years. Let that sink in for a moment. While European naturalists were still debating whether dragons might be real, communities in the South American lowlands had already accumulated generations of detailed, practical knowledge about a creature that outsiders would later struggle to believe existed. These aren't mythological dragons or sea serpents conjured from imagination. These are real observations about real animals, encoded in oral traditions that have survived for longer than most written histories. The Amerindian communities of the Rupununi region, including groups who have inhabited these lands since time immemorial, serve as living repositories of ecological knowledge that no university degree can replicate. When a researcher with a PhD in herpetology arrives in Guyana, they might know everything there is to know about anaconda anatomy, physiology, and evolutionary history. But when it comes to knowing which specific pond is likely to hold a large snake during the late dry season, or recognizing the subtle signs that indicate anaconda presence in an area, or understanding the behavioral patterns that local people have, observed across decades of daily life in this environment, that's knowledge you can only get from people who have been paying attention for generations. An elder from one of the local villages once shared a story that had been passed down in his family for over 60 years. Back when his grandfather was young, there was a pond near their settlement that the community used as a watering hole for their cattle. For several months, livestock kept disappearing from this pond, one animal at a time, vanishing without explanation. The villagers assumed jaguars at first, or perhaps cattle thieves from a distant community. But there were no tracks, no blood, no evidence of a struggle. Animals simply went to drink and never returned. Eventually, a group of men decided to investigate more thoroughly. What they found was a female anaconda of such enormous size that she had apparently made this pond her permanent hunting ground. She would wait submerged in the shallow water near the bank where cattle came to drink, strike with the speed that these supposedly slow animals can muster when motivated, and drag her prey underwater to drown before anyone knew what had happened. The snake was, according to the story, longer than 2 canoes placed end to end, which would put her somewhere in the range of 10 to 12 meters, well beyond what most scientists consider the verified maximum for the species. Now, should we take this measurement literally? Probably not. Storytelling tends to inflate impressive things into legendary things, and a snake that was genuinely 8 meters long might easily become 12 meters in retelling. But the core of the story, a massive anaconda establishing residence at a water source and systematically preying on livestock over an extended period, is entirely consistent with what we know about how these animals behave. The legend preserves important ecological truth even if the specific measurements might be enhanced for dramatic effect. Another story, told across multiple Amerindian communities with slight variations, describes a hunting party that encountered something inexplicable in the deep forest. They had been travelling for days, following game trails through the jungle, when they came upon what appeared to be a wall blocking their path. Not a wall made by humans. There were no cut logs, no construction marks. Just a smooth, curved surface stretching away in both directions as far as they could see, too high to climb over easily, covered in a pattern that seemed almost like scales. The hunters were confused. They followed this wall for an entire day, trying to find its end or a way around it. Night fell, they made camp, and in the morning they continued following the obstruction. It was only on the second day, when they finally reached what appeared to be the end of the wall, that they realized what they had been walking alongside. The wall moved. It was the body of a snake so massive that they had mistaken it for a geographical feature. This story is almost certainly exaggerated. A snake long enough that walking along its body takes 2 days would be hundreds of meters long, which is biologically impossible. But like the cattle pond story, it encodes something true. These communities have encountered anacondas large enough to inspire genuine awe and perhaps genuine terror. The exaggeration isn't random. It's communicating scale in the way that human memory processes extraordinary experiences. When you encounter something that seems impossible, your brain reaches for descriptions that convey the feeling of impossibility. These oral traditions serve multiple practical functions beyond mere entertainment. They identify specific locations where large anacondas have been observed, creating a kind of crowdsourced map of dangerous areas that gets updated across generations. They preserve behavioral observations, hunting techniques, seasonal movement patterns, signs of snake presence, that help community members avoid dangerous encounters, or, conversely, know where to look when they actually want to find one. They encode respect and caution, teaching children from an early age that certain environments demand careful attention. For modern researchers, these indigenous knowledge systems represent an invaluable shortcut through what would otherwise be years of independent discovery. When a village elder says that a particular lagoon always holds large snakes during the month before the rains arrive, that's not superstition. That's data accumulated across multiple human lifetimes of observation. When local guides can look at a riverbank and immediately assess whether anacondas are likely present based on subtle signs invisible to outsiders, they're applying pattern recognition trained by generations of survival necessity. The relationship between these traditional stories and scientific investigation is more complementary than most people assume. Scientists sometimes dismiss indigenous knowledge as folklore contaminated by exaggeration and supernatural beliefs. Indigenous communities sometimes view scientific expeditions as outsiders who think their expensive equipment is more reliable than generations of accumulated wisdom. The truth is that both approaches have blind spots that the other can fill. Scientific methodology excels at precise measurement, controlled comparison, and distinguishing between correlation and causation. When researchers use GPS tracking to document anaconda movement patterns, they're generating data with a precision and reliability that oral tradition cannot match. But they're also operating in a tiny time window, maybe a few field seasons if they're lucky, while trying to understand animals whose behavioral patterns might only become clear across decades of observation. Indigenous knowledge excels at exactly this long-term pattern recognition. The stories about where big snakes appear, when they're most dangerous, how they behave in different seasons, this represents accumulated observation across timeframes that no research grant could ever fund. The knowledge might not come with error bars and statistical significance, but it has been tested against reality for generations. Information that didn't help people survive tends to get filtered out of oral traditions fairly quickly. The most productive expeditions are those that approach indigenous communities as partners, rather than either dismissing their knowledge as primitive or romanticizing it as mystical wisdom. These are people with practical expertise, and like any experts, they respond best to respectful collaboration. When a researcher arrives with genuine curiosity about local knowledge and a willingness to share their own scientific understanding in return, the resulting exchange benefits everyone. The scientists get access to location information and behavioral insights that would take years to develop independently. The local community gets to see their traditional knowledge validated and documented, and often gains valuable information about the animals they share their landscape with. Some of the most significant anaconda discoveries in recent decades have come from exactly this kind of collaboration. Researchers who took the time to listen to local accounts of specific locations where unusually large snakes had been seen. Scientists who followed up on indigenous reports of anaconda behaviors that contradicted the academic literature, and found that the local observers were right and the textbooks were wrong. Expeditions that hired community members not just as guides, but as genuine knowledge partners whose expertise was valued alongside formal scientific training. The legends also tell us something important about how human communities have historically related to these giant predators. Unlike many other dangerous animals that become targets for systematic eradication, anacondas in Guyana seem to have generally been treated with cautious respect rather than fear-driven aggression. The stories emphasize avoidance and awareness rather than killing. There's a kind of coexistence encoded in these traditions, an acknowledgement that humans and giant snakes occupy the same landscape, and that the sensible approach is mutual avoidance rather than conflict. This attitude might seem surprising given the very real danger that a large anaconda can pose, but it makes practical sense when you consider the ecosystem. Anacondas control populations of animals that would otherwise become problems, rodents that damage crops, caimans that threaten fishing areas, wild pigs that destroy forest undergrowth. The indigenous understanding seems to be that these snakes, however frightening, serve a purpose in maintaining balance. Eliminating them would create more problems than it solves. As we move forward into the deeper jungle, armed with our drones and our thermal cameras, we carry with us not just modern technology, but also this accumulated wisdom of people who have been observing anacondas for far longer than science has existed. The combination of both approaches, the precision of contemporary tools and the depth of traditional knowledge, gives us the best possible chance of finding what we're looking for, evidence of just how large these legendary serpents can actually grow. When the sun sets over Guyana's wetlands, a transformation begins that would make any horror movie director jealous. The daytime jungle, with its cacophony of bird calls and visible wildlife, gives way to something entirely different, a realm of shadows, strange sounds, and creatures that have spent millions of years perfecting the art of hunting in complete darkness. This is when the anaconda truly comes alive, and if you want to observe these giants doing what they do best, you're going to need to embrace the night. The problem with nocturnal fieldwork in tropical environments is fairly obvious. Human beings evolved as daytime creatures. Our eyes are absolutely useless once ambient light drops below a certain threshold, and stumbling through a swamp in complete darkness while large predators are actively hunting is what scientists technically refer to as a terrible idea. Flashlights help, but they also announce your presence to everything within visual range, turning you from observer into spectacle. The animals you came to study will either flee from the light or, in the case of certain predators, become very interested in investigating its source. Neither outcome is particularly useful for research purposes. This is where thermal imaging technology transforms from a cool gadget into an absolute necessity. Infrared cameras detect heat radiation rather than visible light, painting a picture of the world based entirely on temperature differences. On a thermal display, warm objects glow in yellows, oranges, and reds. The hotter something is, the brighter it appears. Cooler objects fade into blues and purples, eventually disappearing into the black background of ambient temperature. The result is a ghostly landscape where living creatures stand out like beacons against their cooler surroundings. For mammal observation, thermal imaging is almost unfairly effective. That capybara grazing peacefully near the water's edge? It's a bright yellow blob impossible to miss. The jaguar stalking through the underbrush? A glowing orange phantom moving with predatory purpose. Even birds roosting in trees become visible as warm spots among the cooler foliage. The technology essentially gives researchers superhuman night vision, revealing a world of activity that would otherwise remain completely invisible. But here's where things get interesting. And by interesting, I mean complicated in ways that required researchers to actually think creatively. Anacondas are reptiles, which means they're ectothermic. Their body temperature is determined by their environment rather than generated internally. A snake that's been lying in cool water for several hours will be nearly the same temperature as that water, rendering it almost invisible to thermal cameras. This should theoretically make the technology useless for anaconda research, which would be pretty inconvenient given that we're specifically here to find anacondas. Fortunately, biology provides a workaround. While anacondas can't generate their own body heat, they do absorb heat from external sources. A snake that's been basking on a sun-warmed rock or resting on mud that heated up during the day will retain that thermal energy for hours after sunset. More importantly, the microhabitats where anacondas like to position themselves often have distinctive thermal signatures, warmer patches of vegetation, decomposing organic matter generating bacterial heat, shallow water that absorbed more solar, radiation than deeper areas. Experienced thermal camera operators learn to read these environmental cues, identifying likely anaconda resting spots even when the snakes themselves don't stand out dramatically from their surroundings. The real breakthrough came from understanding how to use thermal imaging in conjunction with other detection methods. A thermal camera might reveal a warm-blooded prey animal acting nervous near a water body, constantly looking in one direction, reluctant to approach the water despite obvious thirst. That behavioral signal, visible through thermal imaging, tells researchers that something is making that animal uncomfortable, and that something is often a predator the camera can't directly see. Following these indirect clues has led to more anaconda sightings than any amount of random searching could achieve. Night operations also revealed something fascinating about anaconda hunting behavior that daytime observations had missed entirely. These snakes don't just wait passively for prey to wander within striking range, they actively position themselves along animal trails, near water access points, and in locations where prey species are likely to pass. They're ambush predators? Yes, but highly strategic ambush predators who seem to understand the movement patterns of their potential meals with remarkable precision. Watching this unfold through thermal imaging is genuinely eerie. You'll see the warm signature of a deer or peccary moving along a familiar trail toward a water source, completely unaware of what awaits. Somewhere in the thermal shadow near the water's edge, a cooler shape lies motionless, patient, positioned, waiting. The warm animal approaches, and then the thermal display erupts into chaos as the strike occurs. It happens so fast that even with technology providing perfect visibility, the initial attack is often a blur. One moment there's a bright warm blob moving toward water, the next moment that blob is thrashing while a cooler mass wraps around it with terrifying speed. The remote-controlled ground vehicles we discussed earlier become particularly valuable during night operations. These miniature rovers, equipped with their own thermal sensors and cameras, can approach anaconda resting sites without triggering the defensive responses that a human presence would cause. The reason this works relates directly to how anacondas perceive their environment, and that requires understanding the remarkable sensory apparatus these animals have evolved. Anacondas hunt using heat detection, specifically through specialized pit organs located along their jaws that sense infrared radiation. This means they can literally see the body heat of nearby animals, creating a thermal image that overlays their regular vision. A warm-blooded creature approaching in complete darkness is clearly visible to an anaconda, not as a visual shape, but as a glowing heat signature that betrays both location and approximate size. It's like having built-in thermal goggles that evolution spent millions of years perfecting. This heat-sensing ability is incredibly sensitive. Anacondas can detect temperature differences of just a few hundredths of a degree, allowing them to pinpoint the precise location of a warm body even when visual conditions are completely useless. The system works passively. The snake doesn't emit anything. It just receives the infrared radiation naturally given off by warm objects. This makes anacondas essentially invisible to their prey until the moment of attack, while their prey remains a clearly visible thermal target throughout the approach. Here's where the technology achieves a kind of elegant victory. Those remote-controlled rovers and underwater robots we deploy, they're made of metal, plastic, and electronics that don't generate body heat. To an anaconda's infrared sensors, a cold machine is indistinguishable from a rock, a fallen branch, or any other piece of environmental debris. The snake's heat-seeking system simply doesn't register the approaching robot as anything worth paying attention to. This allows researchers to achieve something that would be impossible through direct human observation, watching anacondas behave completely naturally while under close surveillance. A person approaching within a few meters would be immediately detected, causing the snake to either flee, become defensive, or simply remain perfectly still until the threat passes. A thermal-neutral robot can roll right up to a resting anaconda, position its camera inches away, and record footage of an animal that has no idea it's being observed. The snake continues whatever it was doing, digesting a meal, waiting in ambush, preparing to move to a new location, while the camera captures everything in unprecedented detail. Night operations have revealed behavioral patterns that decades of daytime research had completely missed. Anacondas apparently engage in what can only be described as patrol behavior, systematically moving through their territory along consistent routes and checking multiple potential hunting sites in sequence. They respond to environmental cues that human researchers are only beginning to understand: subtle changes in humidity, barometric pressure, or the vibrations created by distant animal movement. They display individual personalities, with some snakes being aggressive opportunists who strike at almost anything that passes within range, while others are patient specialists who wait for specific prey types and ignore everything else. The darkness that seemed like such an obstacle at the beginning of this research has become one of its greatest assets. Operating at night, with thermal technology rendering the invisible visible and cold machines approaching where warm humans cannot, has opened a window into anaconda behavior that simply didn't exist before. Every night spent in the field adds new data to our understanding of how these animals actually live, not in artificial captivity, not in brief daytime glimpses, but in their natural element doing exactly what millions of years of evolution designed them to do. Now that we understand how to find and observe these animals, let's talk about what exactly we're looking at. Because the green anaconda isn't just big, it's a masterpiece of evolutionary engineering that has been refined over tens of millions of years into what might be the most efficient large predator on the planet. Everything about this animal, from its skeleton to its skin to its sensory systems, represents solutions to survival problems that most creatures never have to face. Let's start with the obvious: size. The green anaconda holds the title of the world's heaviest snake and competes with the reticulated python for the title of longest. Scientific measurements have confirmed individuals exceeding 9 meters in length, though most adults fall somewhere in the 5 to 7 metre range. The largest documented specimens have weighed over 200 kilograms, roughly the weight of 2 adult humans combined, all of it muscle, bone, and predatory intent. These aren't small animals by any reasonable standard. The skeletal system supporting this mass is both elegant and slightly terrifying. An anaconda's spine contains between 300 and 400 vertebrae, depending on the individual, each one connected to a pair of thin, curved ribs that extend along most of the body's length. That's more than 300 pairs of ribs, compared to the 12 pairs that humans make do with. This extraordinary number of vertebrae and ribs provides the flexibility that allows anacondas to coil around prey, navigate through dense vegetation, and assume the pretzel-like positions they often adopt while resting. On land, all of this anatomy creates some challenges. Without legs to distribute weight, the anaconda's massive body presses down on whatever surface it's resting on, and moving that bulk requires enormous muscular effort. This is why terrestrial anacondas often appear sluggish and reluctant to move. They're not lazy. They're just dealing with the physical reality that dragging 200 kilograms of snake across rough ground is genuinely exhausting work. The snake equivalent of a couch potato, except the couch is wherever they happen to be lying, and the potato is, well, you get the idea. Water changes everything. Buoyancy supports the anaconda's weight, transforming a slow, laborious crawler into a swift, agile hunter. In their aquatic element, anacondas can move with surprising speed, using lateral undulation to propel themselves through the water with an efficiency that their terrestrial movement completely lacks. This is why these snakes are almost always found in or near water bodies. It's not just about hunting opportunity, it's about basic locomotion. The water is where anacondas become the apex predators they evolved to be. The coloration of green anacondas provides camouflage that's effective in both aquatic and terrestrial environments. The base color is an olive or brownish green, overlaid with darker spots and blotches arranged in patterns that break up the snake's outline. In murky tropical water, this coloration makes the anaconda nearly invisible, just another shadow among the submerged vegetation and floating debris. On land, the pattern blends with fallen leaves, mud, and the dappled light filtering through forest canopy. It's not quite as sophisticated as some reptilian camouflage systems, but it doesn't need to be. When you're 9 meters of muscle, hiding in plain sight is more about avoiding detection before striking rather than long-term concealment. The sensory systems of anacondas compensate for what is, frankly, rather poor eyesight. These snakes can see, but their vision is designed for detecting movement rather than resolving fine detail. A stationary prey animal might escape notice entirely, while even slight movement triggers immediate attention. This is why so many prey species freeze when they detect potential predator presence. Evolution taught them that stillness is often the best defense against hunters who rely on motion detection. What anacondas lack in visual acuity, they more than make up for in other senses. We've already discussed the infrared sensing pit organs that allow them to detect warm-blooded prey through heat radiation. But they also possess an extremely sophisticated chemical detection system that works through a combination of conventional smell and something called the vomeronasal organ, or Jacobson's organ. When you see a snake flicking its tongue, it's not tasting the air in any conventional sense. It's collecting chemical particles from the environment and delivering them to the Jacobson's organ in the roof of the mouth. This organ can analyze those particles with extraordinary precision, identifying the species, sex, health status, and recent movement direction of any animal that passed through the area. An anaconda can literally taste where its prey went, following a trail of chemical breadcrumbs that remain detectable for hours or even days after the animal passed by. Then there's the vibration detection system. Snakes don't have external ears, but they can sense vibrations through their body, particularly through their lower jaw when resting on the ground. Footsteps, heartbeats, the splash of an animal entering water, all of these create vibrations that travel through the substrate and alert the anaconda to potential prey or threats. The combination of heat sensing, chemical detection, and vibration awareness creates a multimodal perception system that in many ways exceeds human sensory capabilities. The feeding apparatus deserves special mention because it's genuinely one of the most impressive biological mechanisms in the animal kingdom. Anacondas are constrictors, meaning they kill prey by wrapping coils around it and squeezing until circulation stops and the animal dies from cardiac arrest. They don't crush bones or suffocate victims in the traditional sense. The pressure prevents the heart from pumping, causing death relatively quickly if still quite dramatically. But how does a snake without limbs manage to subdue and swallow animals that can be larger than its own head? The answer lies in a skull structure that sacrifices rigidity for incredible flexibility. The bones of an anaconda's skull are loosely connected by elastic ligaments, allowing the jaw to stretch to remarkable dimensions. The lower jaw isn't fused at the chin like ours, it's two separate bones connected by stretchable tissue, meaning the snake's mouth can expand to a width that seems to violate basic geometry. Swallowing prey is a slow process that can take hours for large meals. The snake alternately advances each side of its jaw, walking its mouth over the prey item in a motion that's been compared to pulling on a tight glove. Powerful muscles assist this process, and the snake's skin stretches to accommodate meals that can be several times the diameter of the snake's resting body. A large anaconda can consume animals as big as deer, capybaras, or caimans, prey that most other predators would need to tear apart piece by piece. After such a meal, the anaconda enters a digestive state that can last weeks or even months. The metabolic demands of breaking down a large mammal are enormous, and the snake's entire physiology shifts to focus on digestion. Body temperature rises slightly, digestive acid production increases dramatically, and the snake becomes essentially comatose, alive but so focused on internal processes that external awareness drops to near zero. During this period, an anaconda that just consumed a 50-kilogram capybara is about as dangerous as a sleeping log. The threat comes before the meal, not after. Understanding this biology helps explain both the danger and the relative safety of anaconda encounters. A hungry anaconda actively hunting is absolutely a threat to be taken seriously. These are powerful predators capable of subduing large mammals, and humans fall well within their prey size range. But the majority of anacondas you might encounter aren't actively hunting. They're digesting, resting, or simply trying to avoid interaction with creatures that are too much trouble to be worth the effort. The legendary man-eating monster exists mostly in imagination. The real animal is a highly efficient but ultimately lazy predator that prefers easy meals to difficult ones. This biological reality forms the foundation for everything that happens when researchers actually encounter these animals in the field, which brings us to the next phase of our expedition, when theory transforms into very physical, very wet, very memorable reality. Knowing where anacondas live is one thing. Actually getting there is an entirely different adventure that deserves its own chapter, because navigating Guyana's interior makes your average wilderness trek look like a stroll through a well-maintained city park. This is a landscape that actively resists human movement, where the concept of roads is more of a philosophical suggestion than a physical reality, and where getting lost isn't just possible, it's practically guaranteed unless you approach the challenge with serious planning and a healthy dose of humility. The fundamental problem is scale combined with similarity. Guyana's interior contains thousands upon thousands of water bodies, rivers, creeks, oxbow lakes, seasonal ponds, permanent lagoons, flooded grasslands that may or may not be navigable depending on recent rainfall. From ground level, these features blur together into an endless repetition of water, vegetation, and more water. That pond where a local elder reported seeing a massive anaconda 30 years ago. It looks exactly like the 300 other ponds within a 10-kilometer radius. Good luck finding it based on verbal directions alone. This is where aerial reconnaissance transforms from a luxury into an absolute necessity. You simply cannot conduct serious research in this environment without eyes in the sky, and modern expeditions have developed sophisticated approaches to the challenge that combine old-school aviation with cutting-edge technology. Picture this: a small ultralight aircraft, barely more than a frame with wings and an engine, buzzing over the Rupununi savanna at an altitude of maybe 500 meters. In the pilot's seat sits someone who knows this landscape intimately, a local aviator who has spent years learning to read the terrain from above, recognizing landmarks that would be invisible to untrained eyes. Mounted on the aircraft's underside is a high-definition camera system with live-streaming capability, transmitting footage directly to researchers on the ground via satellite link. One such pilot, a woman named Rosa, who learned to fly before she learned to drive, has become legendary among research teams for her ability to locate specific water bodies that seem to vanish between visits. She speaks of the landscape the way a chess master speaks of board positions, recognizing patterns, remembering configurations, noticing when something has changed since her last flight. that new channel connecting two previously separate ponds? She spotted it from the air weeks before ground teams discovered it had opened. The water body that mysteriously disappeared from satellite imagery? She found it hidden under a temporary vegetation mat that made it invisible to satellites, but obvious from the right angle at the right altitude. The live streaming camera system represents a significant upgrade from older approaches where pilots would take photographs, land, and then show researchers what they'd found. With real-time video transmission, the ground team can direct the search in progress, asking the pilot to circle back over a promising area, zoom in on a specific feature, or compare what they're seeing with GPS coordinates from previous surveys. It's collaborative reconnaissance that cuts search time dramatically and reduces the frustrating experience of arriving at a location only to discover it's not quite what you were looking for. But here's the thing about aerial reconnaissance. It only gets you to the general vicinity. The plane can identify the pond you're looking for, confirm that it still exists and contains water, maybe even spot some wildlife from above. What it cannot do is deliver you to that location. For that, you need to actually traverse the terrain between your current position and your destination, and this is where things get genuinely challenging. Guyana's road system, such as it is, consists primarily of a single paved highway running along the coast and a handful of unpaved tracks penetrating into the interior. These inland roads are optimistically marked on maps, but their actual condition ranges from rough but passable to theoretical concept rather than physical infrastructure. During the dry season, some of these routes can be navigated by sturdy, four-wheel drive vehicles driven by people who consider road to be a flexible term. During the wet season, the same routes may be underwater, washed out, or transformed into mud pits that swallow vehicles whole and don't give them back. Beyond where the roads give up entirely, travel shifts to boats and feet. Rivers become highways, and the aluminum canoes powered by outboard motors that locals have used for generations become your primary means of transportation. These boats can navigate surprisingly shallow water, slip through narrow channels between vegetation, and access areas that would be completely unreachable by any other means. The skill of the boatmen who pilot them is remarkable. They read the water the way pilots read air currents, anticipating obstacles, choosing the optimal route through seemingly impossible tangles of floating plants and submerged logs. But rivers only go where rivers go, which is not always where you need to be. Reaching many of the most promising anaconda habitats requires leaving the waterways and pushing through terrain on foot, and this is where the expedition pace slows from manageable to geological. The jungle doesn't want you there. It makes this abundantly clear through an endless series of obstacles designed to impede human progress with impressive thoroughness. The vegetation alone presents challenges that people from temperate climates can barely imagine. We're not talking about a pleasant forest walk with occasional brambles. We're talking about walls of interlocking plants, vines, thorny palms, buttress roots, fallen trunks covered in razor-sharp edges that require machete work to penetrate. Progress of a few hundred meters per hour is considered good going in dense jungle. There are documented cases of experienced teams taking entire days to cover distances that would be a casual morning jog on open ground. Then there's the issue of orientation. GPS systems work, technically, but the dense canopy interferes with satellite signals, causing accuracy to degrade exactly when you need it most. Compasses work too, but maintaining a straight bearing while constantly detouring around obstacles is essentially impossible. The local guides who navigate this terrain successfully do so through a combination of landmark recognition, environmental reading, and what can only be described as jungle intuition built from a lifetime of experience. Following someone who knows where they're going makes the difference between reaching your destination and wandering in circles until your supplies run out. The transition zones between different habitat types present their own special challenges. Moving from flooded forest into savanna grassland means adapting to completely different terrain. Leaving a river to traverse seasonally flooded plains requires timing your visit correctly, or finding yourself chest-deep in water that wasn't there during the dry season aerial survey. The landscape that looked so comprehensible from 500 meters altitude reveals layers of complexity at ground level that no aerial photograph can fully capture. Water crossings deserve special mention because they're simultaneously necessary and nerve-wracking. Many routes require fording streams, wading through shallow lagoons, or even swimming across deeper channels while keeping equipment dry. Remember that this is anaconda territory. The the water you're about to enter almost certainly contains snakes, caimans, piranhas, and various other creatures that inspire exactly zero confidence about the wisdom of going for a swim. Most crossings are uneventful, but most is not all, and the knowledge that something large could be lurking just beneath that murky surface adds a certain urgency to the proceedings. Equipment logistics become a serious constraint over extended overland travel. Everything the expedition needs — food, water purification, camping gear, research equipment, medical supplies, batteries for all those gadgets, spare parts for things that will inevitably break — has to be carried by humans through terrain that fights. Every step. Weight limits become critical considerations. That backup drone might save the expedition if the primary one fails, but is it worth the additional load when you're already struggling under 40 kilograms of essential supplies? Every item represents a trade-off between capability and mobility. The smart approach, developed through decades of painful experience, involves establishing a network of base camps that progressively penetrate deeper into the research area. The first camp might be accessible by vehicle or large boat, serving as a logistics hub where supplies can be stockpiled. From there, smaller teams make multi-day forays to more remote locations, carrying only what they need for specific objectives before returning to resupply. This hub-and-spoke model dramatically extends operational range while keeping individual loads manageable. Local communities often play crucial roles in this logistics network. Villages located near promising research areas can provide guides who know the terrain, porters who can carry loads through routes they've travelled since childhood, and local knowledge about conditions that might not be apparent to outsiders. Some expeditions have built long-term relationships with specific communities, returning year after year and contributing to local economies in ways that create genuine partnerships rather than extractive one-time visits. The pace of field research in this environment requires a fundamental mental adjustment for scientists accustomed to laboratory work or even conventional wildlife studies. You cannot rush the jungle. Attempting to maintain urban-style schedules results in exhaustion, mistakes, and sometimes serious accidents. The rhythm of the field becomes dictated by environmental reality rather than arbitrary deadlines. You move when conditions permit, rest when they don't, and accept that some days will accomplish nothing beyond surviving until tomorrow. Weather adds another layer of unpredictability that can derail even the most carefully planned expeditions. Tropical storms can materialize with remarkable speed, dumping enough rain in an hour to flood areas that were dry that morning. When the skies open up, you seek shelter and wait. There's no pushing through a serious tropical downpour. Visibility drops to near zero, trails become streams, and the risks of continuing outweigh any potential benefit. Experienced field researchers build flexibility into their schedules, padding time estimates to account for weather delays that are not just possible but virtually guaranteed. The combination of all these factors means that reaching a specific location in Guyana's interior, a particular pond identified from aerial surveys, mentioned in local stories, or pinpointed by GPS coordinates from previous research, can require days of effort that cover what would be trivial distances on a map. That target just 15 kilometers from your base camp. It might take 3 days to reach, a day to survey properly, and another 3 days to return. A research season that sounds lengthy when planned in an air-conditioned office feels desperately short when measured against the actual pace of field movement. Yet this difficulty is precisely what has preserved both the anaconda populations and their habitat in something approaching pristine condition. The same obstacles that frustrate researchers have protected this ecosystem from the development, hunting pressure, and habitat destruction that have devastated wildlife populations in more accessible regions. The anacondas we're searching for exist because getting to them is so difficult that most people simply don't bother trying. In a sense, the landscape's hostility to human presence is its greatest asset. Understanding this navigation challenge also helps explain why so many questions about giant anacondas remain unanswered, despite centuries of human presence in the region. Local communities have observed these animals for generations, but their knowledge is embedded in oral traditions rather than scientific documentation. Outside researchers face such enormous logistical barriers that comprehensive surveys have been essentially impossible. The animals that do get studied are inevitably the ones in relatively accessible locations, which may not represent the population as a whole. The largest individuals, the true giants that fuel the legends, likely inhabit the most remote, least accessible areas where human disturbance is minimal and resources are abundant. Reaching these locations requires exceptional commitment, substantial resources, and a willingness to accept discomfort and risk that goes beyond what most research programs can justify. The monsters, if they exist, are hiding where almost nobody can go looking for them. With our navigation challenges understood and our approach routes planned, it's time to turn our attention to the remarkable community of species that shares this landscape with the anaconda. Because these giant snakes don't exist in isolation, they're part of an intricate ecosystem where every creature plays a role, and understanding that context is essential to understanding the anaconda itself. Anacondas don't exist in a vacuum. These giant snakes are part of an ecosystem so densely packed with remarkable creatures that the anaconda, despite being genuinely enormous, is just one player in a cast of characters that would make any wildlife documentary producer weep with joy. Understanding this broader community isn't just academically interesting, it's essential for comprehending how anacondas live, what they eat, and why they've evolved into the formidable predators they are today. Let's start by looking up, because Guyana's skies are absolutely crowded with avian life. We're talking about over 800 documented bird species in a country roughly the size of a small European nation, a concentration of avian biodiversity that makes most temperate regions look ecologically impoverished by comparison. From tiny hummingbirds that seem to violate the laws of physics with their hovering abilities, to massive harpy eagles capable of snatching monkeys from treetops, the aerial community above anaconda territory is nothing short of spectacular. Among the most conspicuous of these aerial residents are the vultures, nature's clean-up crew that operates with ruthless efficiency. The turkey vulture, with its distinctive red bald head and wobbling flight pattern, is a common sight circling over the savannas and wetlands. These birds have evolved an extraordinary sense of smell that allows them to detect the chemical compounds released by decomposing flesh from remarkable distances. When something dies in the Guyanese lowlands, turkey vultures know about it within hours, sometimes before the body is even cooled completely. But the turkey vultures are just the first responders. Following them comes the king vulture, a bird so dramatically coloured that it looks like someone designed it specifically to be photographed. Brilliant white plumage contrasts with black flight feathers, while the head displays a riot of oranges, yellows, purples and reds that seems almost obscenely colourful for a creature that makes its living eating dead things. King vultures are larger and more powerful than their turkey vulture cousins, and they use this size advantage to claim priority access at carcasses. The social hierarchy at a corpse is strictly enforced. King vultures eat first, and everyone else waits their turn. For anaconda researchers, these vultures serve as unexpected allies. A circling cluster of vultures in the distance often indicates the presence of a large carcass, which in turn might indicate recent predator activity. Following vulture aggregations has led researchers to anaconda kills on multiple occasions, providing valuable data about what these snakes are eating and how often they're successfully hunting. The birds don't know they're being used as research assistants, and frankly, they don't care as long as there's something dead to eat. Moving from sky to water brings us to another set of remarkable neighbours, the caimans. Guyana hosts several caiman species, but the black caiman deserves special attention because it's essentially the anaconda's main competitor for the title of apex aquatic predator. These crocodilians can grow to 5 meters or more, not quite anaconda-sized, but certainly in the same weight class, and they occupy almost exactly the same ecological niche. They hunt the same prey species, frequent the same water bodies, and occasionally encounter each other in ways that probably don't end with a friendly handshake. The relationship between anacondas and black caimans is complex and not entirely understood. There are documented cases of anacondas killing and eating caimans, which demonstrates the snake's remarkable predatory capability. There are also documented cases of caimans killing anacondas, which demonstrates that the snakes aren't invincible. The outcome of any particular encounter probably depends on size, health, hunger level, and which animal gets the element of surprise. It's essentially a heavyweight title match where both fighters have legitimate claims to the championship, and neither can afford to let their guard down. For practical purposes, the presence of black caimans makes any water body in anaconda territory significantly more interesting and significantly more dangerous. A researcher wading into a pond looking for snakes must also be thinking about crocodilians, because getting tunnel vision about one predator while ignoring another is an excellent way to have a very bad day. The good news, such as it is is that black caimans are generally wary of humans and will usually retreat if they detect an approaching person. The bad news is that usually and always are very different words, and a large caiman defending territory or a nest will absolutely hold its ground. Sharing these waters with the caimans and anacondas are some of the most impressive freshwater turtles on the planet. The giant South American river turtle, known locally as the aral, can grow shells approaching a meter in length and weigh over 50 kilograms. These gentle herbivores congregate on sandbars to lay their eggs in nesting events that attract everything from jaguars to indigenous egg collectors. For anacondas, a large turtle represents a challenging but potentially rewarding meal. The shell provides protection, but the head and limbs that must eventually emerge are vulnerable to a patient predator. The yellow-spotted river turtle is another common resident, smaller than its giant cousin but still substantial by turtle standards. These turtles are often seen basking on logs and rocks alongside caimans, creating tableaux that look like something from a prehistoric diorama. The turtles and crocodilians have apparently reached some sort of understanding. The caimans don't seem to bother the turtles, and the turtles don't seem particularly concerned about sharing basking spots with large predators. It's the kind of interspecies tolerance that humans could probably learn from, though the underlying logic likely involves the turtles being too much trouble to eat and the caimans having easier options available. On land, the cast of characters gets even more diverse. The lowland tapir, looking like a genetic experiment that combined a pig with an elephant and a horse before giving up halfway through, is one of the largest terrestrial mammals in South America. These bizarre-looking creatures can weigh up to 300 kilograms and are primarily active at night, browsing on fruits, leaves, and aquatic vegetation. Their distinctive prehensile snout, that weird trunk-like nose, is actually an incredibly sensitive organ used for grasping food and probably for impressing potential mates, though tapir romantic standards remain poorly documented. Tapirs occupy an interesting position in the anaconda's world. They're too large to be typical prey for most anacondas. Subduing a 300-kilogram animal with kicks, bites, and significant strength is a tall order even for a big snake. But exceptionally large anacondas hunting unusually small or vulnerable tapirs, the possibility exists. More commonly, anacondas and tapirs simply coexist as neighbours who happen to frequent the same water sources without interacting in any dramatic way. The tapir comes to drink and wallow. The anaconda, if present, probably decides that the effort-to-reward ratio doesn't justify an attack. Everybody goes home alive and slightly muddy. The big cats add another layer of complexity to this ecosystem. Jaguars, the undisputed apex land predators of South America, definitely share territory with anacondas and occasionally make meals of them. A jaguar's signature hunting technique, a crushing bite to the skull that penetrates directly into the brain, works just as well on snakes as it does on caimans, capybaras, or anything else unfortunate enough to be identified as food. These cats are phenomenal swimmers, comfortable in water in ways that most feline species are not, which means they operate in exactly the same environments where anacondas are most confident. The puma, slightly smaller than the jaguar but still a formidable predator, adds another variable to the equation. Pumas are more generalist hunters than jaguars, taking a wider variety of prey and adapting to diverse habitats with impressive flexibility. They're present throughout anaconda territory, but tend to avoid direct competition with jaguars where both species overlap. An anaconda encountering a puma would face similar risks to encountering a jaguar. These are animals perfectly capable of killing snakes, though they probably wouldn't bother unless the snake was particularly accessible or the cat was particularly hungry. The ocelot, smaller still but no less beautiful, rounds out the spotted cat contingent. These medium-sized felines hunt primarily small mammals, birds and reptiles, including smaller snake species. An adult anaconda is far too large to interest an ocelot, but the relationship between ocelots and juvenile anacondas is less clear. Young snakes are vulnerable to a much wider range of predators than adults, and ocelots certainly fall within the size range of animals that could make a meal of a meter-long snake. The predator-prey relationships in this ecosystem are not simple linear hierarchies. They're complex webs where the same species can be hunter and hunted depending on age, size, and circumstance. Perhaps the most charismatic of anaconda's neighbours are the giant otters, South America's answer to the question, what if we made otters terrifying? Growing up to 2 meters in length and hunting in coordinated family groups, giant otters are aggressive, vocal, and absolutely not to be messed with. They hunt fish primarily, using teamwork to drive prey into shallow water where it can be easily caught. But they've also been documented attacking caimans, driving off jaguars from riverbanks, and generally acting like the aquatic equivalent of a street gang that owns this neighbourhood and isn't shy about letting everyone know it. Giant otters and anacondas have a complicated relationship. The otter's pack-hunting behaviour and aggressive temperament make them dangerous opponents even for large snakes. There are observations of otter groups mobbing anacondas, driving them away from favoured fishing spots through sheer harassment. On the other hand, a solitary otter or a young animal separated from its group would be vulnerable to anaconda predation. The dynamic seems to favour the otters when they are operating as a unit and favour the snake when individuals can be isolated. It's territorial negotiation through the threat of violence, which is basically how nature handles most boundary disputes. And then there are the capybaras, the world's largest rodents, animals that look like someone dramatically scaled up a guinea pig and forgot to add any survival instincts whatsoever. These gentle social creatures spend their days grazing on grasses and aquatic plants, lounging in shallow water, and generally being the most relaxed animals in an ecosystem full of things that want to eat them. Capybaras are essentially nature's comfort food, and the list of predators that regularly consume them reads like a who's who of South American carnivores: jaguars, pumas, caimans, and yes, absolutely anacondas. For anacondas, capybaras represent something close to an ideal prey item. They're large enough to provide substantial nutrition. An adult capybara can weigh 50 to 60 kilograms, but not so large that they pose significant danger during capture. They're semi-aquatic, spending considerable time in and around the same water bodies that anacondas prefer. They're social and predictable, gathering in groups at favoured locations that an intelligent predator can learn and exploit. And they're frankly not very bright, displaying a level of situational awareness that seems almost suicidally inadequate for an animal living in predator paradise. Watching capybaras and anacondas share a water body is an exercise in observing completely different survival strategies. The capybaras rely on numbers and vigilance. There are always many eyes watching, and when one animal detects danger, the whole group responds. The anaconda relies on patience and concealment, invisible beneath the murky water, waiting for the moment when a capybara ventures just close enough, stays just still enough, for a strike to succeed. It's ambush predation at its finest, and it works often enough that capybaras remain a significant component of anaconda diet throughout their range. The presence of all these species creates an ecosystem in dynamic tension. Predator populations are limited by prey availability. Prey populations are limited by predation pressure, and the whole system pulses with the seasonal rhythms of flooding and drought that reshape the landscape and redistribute its inhabitants. Anacondas sit near the top of this food web, but they're not alone at the apex, and they're certainly not immune to the pressures that govern every other species. Understanding this ecological context helps explain patterns in anaconda behaviour that might otherwise seem mysterious. Why do the larger snakes tend to inhabit the most remote areas? Partly because those areas have less competition from other apex predators and better access to prey populations that haven't been depleted by human hunting. Why do anacondas sometimes appear to avoid certain water bodies that seem perfectly suitable? Perhaps those locations are dominated by large caimans or frequented by jaguar activity that makes them dangerous for snakes. The web of relationships connecting all these species, predator to prey, competitor to competitor, neighbour to neighbour, represents exactly the kind of complex system that takes lifetimes to fully understand. Every research expedition adds new pieces to the puzzle, revealing connections that weren't previously recognised or challenging assumptions that had seemed well established. The anaconda's world is not just a stage where a single actor performs. It's a full-cast production where every performer influences every other, and the show has been running for millions of years. With this ecological context established, we can finally turn to addressing some of the most persistent myths about the anaconda itself, separating the legendary monster from the remarkable but real animal that actually exists in these waters. If you've ever watched a Hollywood movie featuring an anaconda, you probably came away with the impression that these snakes spend their entire existence actively hunting humans with almost supernatural determination. The 1997 film and its increasingly questionable sequels portrayed anacondas as intelligent, vengeful killing machines that could outrun boats, survive explosions, and apparently hold grudges. Spoiler alert, real anacondas do approximately none of these things, and the gap between cinematic monster and biological reality is wide enough to drive a research expedition through. Let's start with the big one, the idea that anacondas are man-eaters constantly on the prowl for human victims. This myth has been around for centuries, predating Hollywood by several hundred years, and it refuses to die despite an almost complete lack of supporting evidence. Documented cases of anacondas killing adult humans are extraordinarily rare. Not uncommon or occasional, genuinely rare to the point where each verified incident becomes international news precisely because it's so unusual. For an animal that has supposedly been terrorizing South American populations since time immemorial, the body count is suspiciously low. The reason for this becomes obvious when you understand how anacondas actually hunt. These are ambush predators that rely on surprise, concealment, and overwhelming force applied to unsuspecting prey. Humans, unfortunately for the monster movie narrative, are terrible targets for this hunting strategy. We're noisy, we travel in groups, we rarely wade blindly into murky water where large snakes lurk, and when we do encounter snakes, we tend to notice them and react with all the subtlety of a fire alarm. An anaconda attempting to ambush a human would need to overcome prey that is alert, intelligent, and likely to fight back in ways that make the whole enterprise not worth the effort. More importantly, anacondas are fundamentally lazy animals in the best possible sense of the word. They're energy-efficient predators that avoid unnecessary exertion with the dedication of a teenager avoiding household chores. Attacking a thrashing, screaming, potentially armed human when perfectly good capybaras are wandering around being oblivious makes zero evolutionary sense. Why take risks when easier meals are readily available? The anaconda's survival strategy is built around minimal effort for maximum return, and humans simply don't fit that equation. The exaggeration of anaconda size represents another persistent myth that distorts public perception. Ask someone who claims to have seen a large anaconda how big it was, and you'll likely get estimates ranging from really big to basically a train with scales. These estimates are almost always wrong, often dramatically so. Studies comparing actual measurements to eyewitness reports consistently show that people overestimate snake length by factors of 50 to 100%. A 5-meter anaconda becomes an 8-meter monster in the retelling. An 8-meter snake transforms into a 12-meter legend. By the time the story has been told a few times, you've got reports of 30-meter serpents that would weigh more than a loaded school bus. This isn't necessarily dishonesty, it's psychology. Encountering a large snake triggers fear responses that affect perception and memory. The brain is not a camera. It's an interpretation machine that prioritizes threat assessment over accurate measurement. When you're staring at an animal that could theoretically kill you, your brain helpfully makes that animal seem even larger and more threatening than it actually is. Add in the tendency for stories to grow with each retelling, the desire to impress listeners with dramatic encounters, and the fundamental difficulty of estimating length for an animal that rarely stretches out straight, and you have a perfect recipe for size inflation. Professional researchers who spend their careers measuring anacondas tell a different story than the barroom storytellers. The largest scientifically verified anacondas top out around 9 meters, which is genuinely enormous, longer than most living rooms, but far short of the 15, 20 or 30-meter behemoths that populate local legends. These verified giants are also extremely rare. The vast majority of anacondas encountered in the wild fall in the 4 to 6 meter range, which is still impressively large but wouldn't generate quite as much internet excitement as the mythical monsters. The man-eating monster narrative also ignores how anacondas actually behave when encountered by humans. One researcher who has spent years studying these animals in the wild describes an encounter with an 8-meter female that perfectly illustrates the gap between legend and reality. The snake was resting in shallow water, clearly visible, completely aware of the approaching humans. According to every horror movie ever made, this should have been the setup for a terrifying attack scene. Instead, the snake did essentially nothing. It lay there, calm and apparently unbothered, as the researcher approached, observed, and eventually made physical contact. The researcher described the experience as interacting with an animal that was docile and completely relaxed, adjectives that don't exactly align with the bloodthirsty killer of popular imagination. The snake tolerated handling, showed no defensive aggression, and eventually slid away into deeper water at its own pace when it apparently decided the interaction had gone on long enough. Not the behavior of an apex predator eager to add human to its diet, but rather the behavior of an animal that correctly assessed the situation as not worth getting worked up about. This calm demeanor is particularly pronounced in recently fed anacondas, and here's where we need to understand just how the anaconda digestive system works. When one of these snakes consumes a large meal, say a 40-kilogram capybara, the digestive process that follows is nothing short of a biological marathon. The snake's metabolism ramps up dramatically, dedicating enormous energy to breaking down what might be several months' worth of nutrition in a single sitting. Digestive acids increase in potency, organs that were essentially dormant between meals spring into action, and the snake enters a state that's less resting and more processing. During this digestive period, which can last weeks or even months, depending on meal size and environmental temperature, the anaconda becomes almost completely inactive. It finds a secure location, ideally warm, protected, and close to water, and stays there. Moving requires energy that should be going to digestion. Hunting is off the table because the snake physically cannot accommodate another meal until the current one is processed. Even defensive behaviors are suppressed because fighting burns calories that are needed elsewhere. A digesting anaconda is, for all practical purposes, a large, scaly log. It poses essentially zero threat to anything that doesn't actively try to harm it first. You could probably walk past one, sit next to one, maybe even trip over one, and the snake's response would be to continue lying there digesting. This is not an animal in any condition to chase down prey or engage in dramatic confrontations. The most it might do is hiss or make slow defensive movements if directly molested, but even that requires effort it would rather not expend. Understanding this feeding biology completely reframes the danger calculus around anaconda encounters. A hungry anaconda actively hunting in its preferred habitat at the optimal time of day represents a genuine, if still quite small, threat to humans who wander into the wrong place at the wrong time. But what percentage of anacondas are in active hunting mode at any given moment? Given that they can survive months between meals and spend most of their time resting, the answer is not many. The vast majority of anacondas a person might encounter are either recently fed and therefore harmless, or well camouflaged and therefore invisible. The narrow window of hungry enough to hunt but visible enough to encounter is surprisingly small. None of this means that anacondas are cuddly pets, or that people should approach them casually. A sufficiently large anaconda defending itself can absolutely cause serious injury or death. Wild animals deserve respect, and respecting anacondas means giving them space, avoiding obvious ambush sites, and not doing anything stupid like trying to handle them for social media content. But the monster of legend, the relentless hunter that views humans as preferred prey, simply doesn't exist outside of Hollywood screenwriters' imaginations. The real anaconda is far more interesting than the myth. It's an animal superbly adapted to its environment, capable of taking down large prey through patience and power, but also fundamentally conservative in its energy expenditure and threat assessment. It's a creature that has survived essentially unchanged for millions of years by being very good at exactly one thing: waiting for the right opportunity and then capitalizing on it with overwhelming force. Not dramatic, not cinematic, but incredibly effective. If you thought anaconda behavior was fascinating during hunting and feeding, wait until you hear about what happens when breeding season arrives. Because the reproductive rituals of these snakes involve spectacles so bizarre that early European explorers who witnessed them probably questioned their own sanity. We're talking about multiple snakes intertwined in writhing masses that can last for weeks, scenes that likely contributed to some of humanity's strangest monster myths. Anaconda mating season typically coincides with the late dry season and the onset of the rains, roughly April through May in Guyana. This timing isn't accidental. The transition between seasons creates optimal conditions for the energy-intensive process of reproduction, and it ensures that offspring will be born when prey is abundant and growing conditions are favourable. Evolution doesn't do random. Every aspect of anaconda reproductive timing has been optimized over millions of years of natural selection. The process begins when females, having spent months building up fat reserves through strategic hunting, begin releasing pheromones that signal their reproductive readiness. These chemical signals are extraordinarily potent, detectable by male anacondas from remarkable distances. A receptive female essentially broadcasts her availability to every male within a multi-kilometre radius, and the response can be dramatic. Males that might normally stay in their established territories suddenly become motivated travellers, following pheromone trails with single-minded determination. The distances these males will cover in pursuit of breeding opportunities are genuinely impressive. GPS tracking studies have documented male anacondas traveling 10, 15, even 20 kilometers during mating season, distances that would represent weeks of movement under normal circumstances compressed into days of urgent travel. The biological imperative to reproduce apparently overrides the normal anaconda preference for minimal effort. Evolution cares about one thing above all else: making more anacondas. Everything else is secondary. When multiple males converge on a single receptive female, the result is what scientists formally call a breeding ball, and what anyone watching would probably call absolute chaos. A typical breeding ball involves one female at the center, with anywhere from 2 to over a dozen males wrapped around her in a tangled mass of scales, muscle, and reproductive desperation. The males compete for position, each trying to align his body with the female's cloaca, the opening used for both waste elimination and reproduction, while simultaneously preventing other males from achieving the same goal. Watching a breeding ball in action is simultaneously fascinating and slightly disturbing. The mass of snakes moves continuously, with individual males constantly adjusting position, pushing against rivals, and attempting to maintain their place in what must be an exhausting competition. The snakes don't fight in the conventional sense. There's no biting or visible aggression, but the physical competition is intense nonetheless. Larger, stronger males have obvious advantages, but smaller males can sometimes succeed through persistence, positioning, or simply lasting longer than competitors who exhaust themselves early. The duration of these breeding balls defies reasonable expectations. We're not talking about a few hours of activity followed by everyone going their separate ways. Breeding balls have been documented lasting for days, sometimes weeks, with the participating snakes remaining intertwined almost continuously. The males apparently eat nothing during this period, devoting all their energy to the competition for mating rights. The female, positioned at the center of all this attention, presumably has mixed feelings about the whole arrangement. From a distance, a large breeding ball presents an appearance that must have terrified early observers who didn't understand what they were seeing. Imagine stumbling through the jungle and encountering what appears to be a single massive snake with multiple heads, writhing and moving in ways that seem to defy the anatomy of any single animal. The legendary multi-headed serpents that appear in mythologies around the world, the hydras, the nagas, the various many-headed dragons of European folklore, might well trace their origins to misinterpreted observations of snake-breeding aggregations. The possibility becomes even more compelling when you consider how breeding balls eventually disperse. After days or weeks of competition, mating eventually occurs, sometimes with multiple males achieving copulation with the same female over the course of the event. When the female has had enough, or when the males finally exhaust themselves, the ball begins to separate. But this dispersal isn't instantaneous. The snakes disentangle slowly, reluctantly, with individual animals peeling away from the mass over a period of hours. An observer watching a breeding ball disperse would see what appears to be one impossibly large snake gradually splitting into multiple smaller snakes. Combined with the multi-headed appearance of the intact ball, this transformation could easily generate stories about enormous serpents of fantastic proportions. That legend about the hunting party that walked for 2 days along what they thought was a snake's body? Perhaps they encountered an extended breeding ball stretched across the landscape, with multiple snakes positioned end-to-end, creating the illusion of a single impossibly long animal. The mechanics of anaconda reproduction involve some additional details that are worth mentioning for their sheer biological weirdness. Male anacondas possess paired reproductive organs called hemipenes, which are normally stored internally and averted only during mating. The female can apparently exercise some selectivity about which male actually fertilizes her eggs, storing sperm from multiple males and preferentially using genetic material from preferred partners. This means that even males who successfully mate might not actually father offspring. The female maintains final control over reproduction, despite being mobbed by eager suitors. After mating concludes, females carry developing embryos internally for about 6 to 7 months before giving live birth. Anacondas are ovoviviparous, meaning the eggs develop and hatch inside the mother's body, with fully formed baby snakes emerging ready to swim and hunt. Litter sizes vary dramatically, from a dozen offspring to over 80 in exceptional cases. Larger females tend to produce larger litters, which creates strong evolutionary pressure favouring female body size, one reason why female anacondas grow so much larger than males. The baby snakes, each about 60 to 90 centimetres long at birth, receive no parental care whatsoever. The mother essentially expels them and immediately goes back to her own survival priorities. From their first moments of independent existence, juvenile anacondas must hunt, hide, and avoid the numerous predators that view them as convenient snacks. Mortality rates for young anacondas are extremely high, with the vast majority falling to predation, starvation, or disease before reaching adulthood. Those that survive grow rapidly during their first few years, taking progressively larger prey as they increase in size. The breeding bull phenomenon remains one of the most spectacular wildlife events that most people have never heard of. It doesn't get the documentary coverage of African migrations or whale breeding grounds, partly because the remote locations make filming difficult, and partly because writhing snake masses don't have quite the same family-friendly appeal as frolicking elephant calves. But for those researchers fortunate enough to witness one, it represents a window into anaconda behaviour that reveals these animals as far more complex and interesting than their reputation as simple ambush predators might suggest. Understanding anaconda reproduction also helps explain population dynamics and conservation concerns. These animals reproduce relatively slowly compared to many snake species. A female might only breed every 2 or 3 years, and high juvenile mortality means that few offspring survive to reproduce themselves. Populations can't bounce back quickly from hunting pressure or habitat loss. The giant anacondas that fuel legends represent the successful survivors of a brutal selection process, animals that manage to avoid predation, find sufficient food, and reach breeding size over periods of 10 to 15 years or more. With our understanding of both anaconda myths and realities now reasonably complete, we can turn to examining how humans and these remarkable snakes have coexisted across centuries of shared history, and how that relationship might evolve in the future. The story of Guyana is, at its core, a story about sharing space with things that can kill you. For thousands of years, human communities have carved out existence in a landscape dominated by jaguars, caimans, venomous snakes, and yes, giant anacondas. This isn't the sanitized coexistence of a nature documentary where everything maintains respectful distance. It's the messy, complicated reality of predators and prey, livestock losses and retaliatory killings, fear and fascination intertwined in ways that outsiders rarely appreciate. The cattle ranches that dot Guyana's interior exist in a state of constant negotiation with the surrounding wilderness. Ranchers lose animals to predators every year, sometimes a few, sometimes more than they can afford. A jaguar develops a taste for calves and suddenly becomes a recurring nightmare. A caiman takes up residence in a watering pond and claims livestock that come to drink. An anaconda, as we discussed earlier, establishes itself near water sources and systematically picks off animals that venture too close. These losses aren't abstractions to the people who experience them. They're economic devastation for families operating on thin margins, and they're personal losses for people who often know their animals individually. The emotional response to predator attacks is understandable and deeply human. When something kills your livestock, your livelihood, your security, your children's future, the natural impulse is to kill it back. For generations, this is exactly what happened. Large predators that threatened human interests were hunted, trapped, poisoned, and eliminated whenever possible. The logic was simple. Fewer predators meant fewer losses, and anyone who suggested otherwise clearly hadn't watched their cattle disappear one by one into the jaws of something that didn't care about property rights. This approach worked in the short term for the humans involved. Problem animals were removed, losses decreased temporarily, the immediate threat was addressed. But ecosystems are not simple machines where you can remove components without consequences. The predators being eliminated weren't just threats, they were also regulators. They controlled populations of prey species that, without predation pressure, could explode in numbers and create entirely new problems. They removed sick and weak individuals, maintaining the genetic health of prey populations. They shaped behavior patterns that kept the whole system in balance. The relationship between local communities and giant anacondas encapsulates this tension perfectly. On one hand, these snakes occasionally take livestock, generating fear and financial loss. On the other hand, they control populations of wild animals that would otherwise compete with livestock for grazing and water resources. They take caimans, which might otherwise become numerous enough to pose serious threats to people and animals. They're part of a web of relationships so complex that removing them creates ripples no one can fully predict. For most of history, this complexity was invisible to the people making decisions about predator control. You saw the jaguar killing your cow. You didn't see the cascading ecological effects of eliminating jaguars from the landscape. Scientific understanding of ecosystem dynamics is relatively recent, and translating that understanding into practical policy that works for people who actually live with predators is an ongoing challenge. Telling a rancher who just lost a month's income to a snake that, actually, anacondas are ecologically important doesn't pay his bills or feed his family. Modern conservation approaches try to navigate this impossibly difficult terrain by finding ways to reduce conflict without eliminating either the predators or the human communities. This might mean improving livestock management to reduce vulnerability, better fencing, more vigilant herding, avoiding the most dangerous watering spots during high-risk periods. It might mean compensation programs that help absorb the financial impact of predator losses. It might mean developing alternative income streams like ecotourism that make living predators economically valuable rather than purely costly. The research expeditions that venture into Guyana's anaconda territory represent a different kind of intervention, one focused on understanding rather than control. When scientists arrive with their drones and GPS trackers and underwater cameras, they're not there to solve the anaconda problem by eliminating anacondas. They're there to learn. Where do these animals actually live? How do they behave? What can we discover that might help humans and snakes share the landscape more successfully? This shift in approach, from hunting monsters to studying them, reflects a broader change in how Western science thinks about large predators. The old paradigm saw predators as competitors to be eliminated, threats to human dominance that needed to be controlled through force. The new paradigm, emerging gradually over the past century and still far from universally accepted, sees predators as essential components of functional ecosystems, animals that serve crucial roles, and whose loss creates problems that often exceed whatever benefits their elimination provided. Technology has been crucial in enabling this more nuanced approach. The non-invasive observation methods we've discussed throughout this documentary, the drones, the thermal cameras, the underwater robots, the GPS tracking, allow researchers to study anaconda behavior without constantly disturbing the animals or putting researchers at risk. In the past, studying large predators often meant capturing them, handling them, sometimes killing them for specimens. Now we can observe from safe distances, gathering data that would have been impossible to collect using older methods. This technological capability matters because it changes what knowledge is possible. When you can track an individual anaconda's movements over months or years without ever touching the animal, you develop understanding that capture-based studies could never provide. When you can observe hunting behavior at night using thermal cameras rather than stumbling around with flashlights, you see behaviors that previous researchers never documented. When you can survey vast areas by drone rather than hacking through jungle on foot, you find animals in locations that would otherwise remain unknown. The knowledge generated by these studies filters back into practical applications. Understanding where anacondas concentrate during different seasons helps communities avoid high-risk areas at high-risk times. Knowing what prey species anacondas prefer allows predictions about which livestock are most vulnerable and what management changes might reduce losses. Documenting the ecological role of these predators provides arguments for their conservation that go beyond abstract appeals to biodiversity and speak to practical concerns about ecosystem function. Indigenous communities in Guyana have always had their own approaches to coexisting with dangerous wildlife, developed over millennia of practical experience rather than decades of scientific study. These approaches tend to emphasize awareness, avoidance, and respect rather than elimination. The traditional relationship between Amerindian communities and anacondas involves knowing where the snakes live, recognizing the signs of their presence, and organizing activities to minimize dangerous encounters. It's coexistence based on knowledge rather than control, the same principle that modern conservation science is gradually rediscovering. The convergence of traditional ecological knowledge and contemporary scientific methods represents something potentially powerful. When researchers work with indigenous communities rather than merely studying their environment, the combination of detailed local knowledge and technological capability produces results that neither could achieve alone. The elders who know which pond holds large snakes contribute information that would take researchers years to discover independently. The scientists with GPS trackers can verify and extend that knowledge in ways that traditional observation cannot. The partnership, when it works, generates understanding that serves both conservation goals and community interests. But the challenges of human-wildlife coexistence in Guyana are far from solved. Economic pressures push people into increasingly close contact with wildlife habitat. Climate change alters the seasonal patterns that both humans and animals have adapted to over generations. Global markets for wildlife products create incentives for exploitation that can quickly overwhelm local conservation efforts. The anaconda's future, like the future of large predators everywhere, depends on humans deciding that sharing the planet with these animals is both possible and worthwhile. What the research expeditions demonstrate, perhaps more than any specific scientific finding, is that understanding changes relationships. People who have actually observed anacondas, who have seen these animals behaving in their natural environment, who have touched the remarkable biology of a 9-meter snake and watched breeding balls form and disperse, these people rarely come away wanting to eliminate anacondas from the world. The experience creates respect, appreciation, and often genuine affection for animals that were previously known only through fear and legend. This transformation of perspective might be the most important outcome of scientific engagement with large predators. Not the data collected or the papers published, but the shift in how people think about creatures they once saw only as threats. When a rancher who has lost cattle to anacondas meets a researcher who has spent years studying these animals, and they talk about what the researcher has learned, something changes. The snake becomes more than a monster. It becomes an animal with behaviors, life history, ecological relationships, and perhaps even a kind of dignity that demands consideration. After all the planning, all the technology deployment, all the sweat and mosquito bites and equipment failures, what did our expedition actually accomplish? The temptation is to answer in numbers: snakes counted, measurements taken, GPS points logged, hours of footage recorded. And yes, those numbers exist, filling spreadsheets and databases that will keep analysts busy for months. But the true discoveries of an expedition like this can't be reduced to statistics. The single most profound outcome of spending time in anaconda territory is the encounter itself. The moment when you're actually face to face with one of the largest snakes on Earth, watching it breathe, seeing the light reflect off its scales, feeling the sheer physical presence of an animal that could theoretically kill you but has apparently decided not to bother. That experience changes something fundamental in how you think about these creatures and your place relative to them. One expedition member, a wildlife biologist with 20 years of experience working with large reptiles, described her first encounter with a genuinely massive anaconda as like meeting royalty, not human royalty, but something older and more significant. The snake, an estimated 8.5 meters of coiled muscle resting in the shallows of a remote lagoon, displayed the calm indifference that we've discussed throughout this documentary. It acknowledged the approaching humans with a slow turn of its head, assessed them as neither prey nor threat, and resumed its rest. The humans, for their part, stood in respectful silence, documenting what they could while trying to process an encounter that felt genuinely humbling. The measurements from that encounter, obtained using laser range-finding equipment and careful photogrammetric analysis, placed the snake among the largest ever scientifically documented. But here's the thing, and this is what the expedition members universally emphasized when discussing their experiences: the number didn't capture what made the encounter meaningful. A snake measuring 8.47 meters versus 8.52 meters doesn't change the fundamental experience of being in the presence of something that remarkable. The precision of modern measurement technology almost seems beside the point when you're standing in a Guyanese swamp, watching a creature that has been essentially unchanged since the age of dinosaurs. What the expedition did confirm, through multiple encounters and extensive observation, is that the anaconda's reputation requires serious revision. These are not the aggressive monsters of Hollywood imagination. They are overwhelmingly cautious animals that prefer avoidance to confrontation and that pose minimal threat to humans who behave sensibly in their presence. This finding isn't new, researchers have been saying it for decades, but documenting it repeatedly, with modern equipment generating footage and data that can't be dismissed, adds weight to arguments for conservation that have previously struggled. Against deeply ingrained fear, The expedition also documented several breeding balls, providing some of the most complete footage ever captured of this remarkable behavior. Watching multiple snakes intertwined in their strange reproductive choreography, the researchers couldn't help but imagine how early observers might have interpreted what they were seeing. A mass of snake bodies with multiple heads, writhing and moving as a single entity, periodically separating and reforming. If you didn't know what you were looking at, you might easily conclude that you'd encountered some kind of multi-headed monster. The ancient myths suddenly seem less like fantasy and more like reasonable interpretation of genuinely bizarre reality. One particularly large breeding ball, documented over a period of 11 days, involved at least 14 males competing for access to a single enormous female. The female's size, estimated at over 7 meters, made her the dominant presence at the center of the mass, with smaller males wrapped around her in layers that sometimes completely obscured her body. When the ball eventually dispersed, the snakes separating and moving off in different directions, the researchers calculated that the combined length of all participants exceeded 100 meters. A single photograph of the intact ball, with multiple heads visible emerging from the tangled mass, looks like an illustration from medieval mythology brought to life. This observation provides a compelling explanation for some of the most outlandish reports in the historical record. Those stories about snakes so long that parties walked for days along their bodies? Perhaps they encountered extended breeding aggregations rather than single impossible animals. The legends of multi-headed serpents that plagued ancient travellers. Perhaps they witnessed exactly what our expedition documented. Real animals engaged in real behaviours that happened to look utterly fantastic to anyone unfamiliar with anaconda reproduction. The expedition's findings also emphasised how much remains unknown about these animals. For all our technological capability, we've barely scratched the surface of anaconda biology and behaviour. The most remote portions of their range remain essentially unstudied. The largest individuals, the ones most likely to push the boundaries of what we think these animals can achieve, probably live in places that even the most determined expeditions can't reach. Every question answered by the research generated 3 new questions that will require future expeditions to address. Guyana itself emerged from the expedition as something more complex than the simple, pristine wilderness narrative that outsiders often project onto remote regions. This is a landscape shaped by human presence stretching back millennia, where indigenous communities have developed sophisticated relationships with the natural world that Western science is only beginning to appreciate. It's also a landscape facing genuine threats from development pressure, climate change, and the global economy's insatiable appetite for resources. The anacondas we studied exist in a window of relative stability that may not remain open indefinitely. Perhaps the most important revelation of the expedition is simply this: Guyana rewards those who approach it with curiosity and respect rather than fear and aggression. The researchers who waded into anaconda territory armed with cameras instead of weapons discovered animals willing to tolerate close observation. The expeditions that partnered with indigenous communities rather than dismissing local knowledge found guides whose expertise exceeded anything that could be learned from academic training. The approach of patient investigation, replacing the approach of conquest and control, yielded understanding that generations of monster hunters never achieved. The giant anaconda remains in many ways as mysterious as it was when the first European explorers reported encountering enormous snakes in the South American lowlands. We know more about their biology, their behaviour, their ecological role than ever before. But the fundamental questions, how large can they actually grow, how many exist in the most remote refuges, what aspects of their lives remain completely undocumented, will keep researchers coming back to Guyana for generations to come. For now, the anacondas continue doing what they've done for millions of years, waiting in the murky waters of tropical lowlands, detecting the approach of prey through senses we're only beginning to understand, and occasionally reminding humans that we share this planet with creatures far older and in some ways far more successful than ourselves. The monsters of legend turn out to be remarkable animals deserving of study, protection, and perhaps even admiration, and the jungle keeps its secrets, revealing them only to those patient and humble enough to look carefully. So there you have it, the real story of the giant anaconda, stripped of Hollywood special effects and explorer exaggerations. An animal that's genuinely extraordinary, without needing to be a supernatural threat. A landscape that challenges everything you thought you knew about wilderness. and a reminder that the most interesting discoveries often come not from seeking monsters to conquer, but from approaching the unknown with an open mind and a willingness to be surprised. If you've made it this far, you're clearly the kind of person who appreciates a deep dive into something genuinely fascinating. Smash that subscribe button if you want more content like this, and drop a comment letting me know what other creatures or places you'd like me to explore. Until next time, stay curious, stay respectful, and maybe think twice before wading into murky South American waters. Thanks for watching.